When atoms or molecules absorb energy, that energy is often released as light energy. And we observe this in fireworks and neon lights, in these fluorescent lights even. If we take the light that's emitted from a heated object or a heated substance and pass it through a prism, we do not get a beautiful full rainbow all the time. We get what's called an emission spectrum. So emission, because this is light that is emitted from the substance. This spectrum will not be continuous. It's going to have bright lines at specific wavelengths with darkness in between. And it's a little bit like a barcode for the element. It's going to be specific for each element. We can use it to identify the element. And classical physics cannot explain why this happens. So here we have an example of gases emitting light. Here we've got a mercury lamp, a helium lamp, and a hydrogen lamp. Inside of these glass tubes is mercury, helium, and hydrogen gas. And there's a voltage being applied across the end, so energy is being given to those gas atoms or molecules, and in response to that input of energy, they give off light. If we take the light from a lamp like this and pass it through a prism, we see a series of lines. Each element is going to have a particular color of light that it emits. So you can make a mercury lamp, and every time you make a mercury lamp, it's going to give off that same color. We also observe that elements will give off light when placed in a flame. So if we have a solution of sodium ions and we put it on a wire and we stick it into a Bunsen burner flame, we see this flash of color, this really intense yellow color. Potassium is harder to see, but it will give this nice lavender color. Lithium gives sort of a scarlet red, and barium, that doesn't show up either place very well. It's actually got kind of a greenish color to it. And so this is one way that elements can be identified, is by the flame test, because they give off a particular color of light when they have an input of energy. So what we can do is we can take the light from, say, a hydrogen lamp, pass it through a slit to focus it, and then pass it through a prism. If we're doing this with sunlight, what we're going to see over here is a continuous rainbow. But from a hydrogen lamp, we see a few discrete lines. They are separated by their wavelengths, just like continuous white light would be. If we passed white light through here, the orange would be in the same place, and the violet would be over there, because the position of it on this screen depends on its wavelength. But for hydrogen, there are only lights with, the light only contains these particular wavelengths. And so we only see 4 lines of color. Here's the helium spectrum, a little more complicated. Barium is more complicated than that. Here's white light. This is what the sunlight looks like. You see a continuous spectrum. Oxygen and neon. Neon's got lots of lines in here. So those are examples of emission spectra of elements.
Is there any kind of pattern with mass?
Is there a pattern with mass? About the only pattern I could say is that the higher the mass, the more complicated and the more lines there would be, generally. You can have an emission spectrum. You can also have an absorption spectrum. And this is showing the emission spectrum of mercury. This is the absorption spectrum. If you shine continuous light on mercury, it will absorb in those same wavelengths that it would emit if you energized it. So that's kind of interesting. So emission and absorption, same wavelengths, they're just opposite. Well, Johannes Rydberg, actually I think it's Rydberg. Johannes Rydberg, he lived around the turn of the 20th century. He looked at these atomic spectra because scientists discovered this, and they're like, okay, wow, that's not what we were expecting. What do we do with this? What does it mean? Can we find a mathematical relationship between these lines? So he studied these lines, and he found that they could be described by an equation that involved an inverse square of integer numbers. It's called the Rydberg Equation. The thing about it is it doesn't really tell us what's going on or why elements do this. The atomic spectra are discrete. The atoms are stable. His equation works, but it doesn't really give us much information. So here's his equation for what it's worth. 1 over the wavelength is equal to the Rydberg constant times the quantity 1 over m squared minus 1 over n squared. M and n are integers. So, just coming up with this equation is quite an accomplishment in and of itself. So, we have to venture back towards Rutherford's nuclear model of the atom. The atom contains a tiny dense center called the nucleus. The nucleus essentially contains all the mass of the atom. Remember, the nucleus is where the protons and the neutrons are. Outside of it are the electrons. Do you remember the plum pudding model and the shooting the things through the gold foil? Okay, this is that same kind of stuff we're talking about. The nucleus is positively charged, and the amount of positive charge balances the negative charge of the electrons. The electrons are moving around in the empty space of the atom surrounding the nucleus. The really big question is, what are the electrons doing? How are they moving around? Well, there are problems with Rutherford's model. One of them is that electrons are charged particles. And according to classical physics, Newtonian physics, moving charged particles give off energy. Therefore, the electrons should be giving off energy, and that should cause the atom to glow, but it doesn't. The electrons should be losing energy. They're giving off energy. The energy of the universe is constant. That energy has to come from somewhere. They could only have so much energy, and if they're losing it, then they're going to become less energetic, and they should crash into the nucleus, and the atom should collapse, but it doesn't. Classic physics doesn't explain how the atom can be stable. The nuclear model, Rutherford's nuclear model, doesn't explain what structural changes are happening in an atom when it gains or loses energy. We see evidence from the interaction with energy and light that something is happening inside of an atom, and it's giving off light. So Niels Bohr developed a model of the atom to explain what's going on when we see these transitions, these energy transitions. The major ideas of his model were that the energy of the atom is quantized, meaning there's discrete amounts. So whether you recognize it or not, we experience quantized and continuous things in real life. And I don't think, there's not. If we think about stairs versus a ramp, I'll just make a new thing here. So if we have, here's the sidewalk, here's the ground, and if we have a ramp, or if we have a set of stairs. And we're talking about how high above the ground are you? Well, a ramp is continuous. You could be right here, you could be right there, you could be just a teeny tiny bit further up. You could be at any height above the ground on this ramp. Stairs are quantized. You can be on the first step, or you can be on the second step. You cannot stand in between steps. It's not possible. So, if this is 1 foot and 2 feet and 3 feet and 4 feet, you can't be 2.75398 feet above the ground on the stairs. You can be 2 feet or 3 feet, nowhere else. There are discrete levels, and it only comes in those amounts. Continuous means that anything is possible. So a piano keyboard is continuous. You can hit the C key or the C sharp key, but you cannot make a note that's in between those tones. A violin is continuous. You can put your finger anywhere on the string, and you can make this sliding. I think I play both the violin. Well, I used to play the violin when I was a child. Played that, still play the piano sometimes. So I know from personal experience with a violin, you can make horrendous sounds, okay? Screechy, horrible sounds. But part of why you can make horrible sounds is because you can make notes that aren't notes in music. You can make sounds that are not A or B. They're in between. Okay? So it's just important to understand the difference between something that's continuous and something that's quantized. Something that is quantized, there are specific levels, and you can only be at those levels. There's no way to be in between. Any questions? So let's go back to the slide. So in Bohr's model, the energy of the atom is quantized, meaning the atom can have X amount of energy or it can have Y amount of energy, but it can't have an energy that's in between. The amount of energy in the atom is related to the position of the electrons in that atom. So quantized means that the atom can only have very specific amounts of energy. In Bohr's model, it resembles the solar system, in which the electrons are traveling in orbits, stationary states, that are at a fixed distance from the nucleus. So you think about, the Earth orbits the sun, right? And we're in this particular orbit, and our orbit doesn't change. We're not going to get into astronomy. Basically, we have a fixed orbit. The electrons travel in orbits that are at a fixed distance. You can be X distance from the nucleus, or you can be Y distance from the nucleus, but nothing in between. They're quantized. Electrons emit radiation when they jump from an orbit with higher energy to an orbit with lower energy. So if they go from a high energy orbit, they've got high energy, they go to a lower energy orbit, where does the energy go? Well, it gets spit out as a photon of light. They emit light with a particular energy, a particular wavelength. The emitted radiation is a photon or a packet of light, because light can act as particles. The distance between the orbits is going to determine the energy of the photons of light that are produced. Have you heard of quantum leap? There used to be a show called Quantum Leap. But the concept of quantum leap is you can be in one place, or you can be in this other place, but you got to the other place without traveling through space in between. And that's what's going on with these electrons, is they are never observed between states. They are in one state or in the other, never in between. And this is tied into that whole dual superposition of states kind of thing. But that's called a quantum leap. So the energy of that photon is the difference between those two stationary states for the electron. We can calculate the energy of those states from the wavelengths of the light. We can measure the wavelength of the light, calculate the energy of the light. The energy of the light is equal to the energy difference between the two states of the electrons. Okay, this is somebody thinking about a problem. So the Bohr model was awesome. They calculated the energies of those different states from the spectral lines. the problem was it only worked for hydrogen. You got a picture here? Here's a picture. Yeah, we need this picture. Okay, so here's an illustration. This has great historical significance, and the reason we still teach it to you is it also has conceptual importance. It helps us to begin to think about this strange world inside of an atom. So the Bohr model says here's the nucleus, here's energy level 1, the first orbit, the second orbit, the third, the fourth, the fifth, and each of these has a specific amount of energy. So when we take that emission spectrum for hydrogen, and we see this violet light with a wavelength of 434 nanometers, that corresponds to the energy difference between level 5 and level 2. The electron can be in level 5, and when it goes down to level 2, the energy change is equal to this, and it shoots out a photon of light of that energy. The blue-green line that we see corresponds to a transition from 4 to 2, and the red one corresponds from 3 to 2. Now, there are other transitions that are occurring, but the energy difference between those may not fall within visible light spectrum, and so then we wouldn't be able to see it, but they could still be happening. So in this model, we envision the electron having a quantum leap. Say you zap this with electricity, and the electron jumps up to level 5. Well, it's not stable up there, and eventually it's going to go back down. As it goes down, it's going to spit out the energy that it received, and we'll see that as visible light. So, great historical and conceptual importance, but ultimately replaced by the quantum mechanical model. The problem is, Bohr's model only worked for hydrogen. It didn't even work for helium. But he was able to calculate all this really cool stuff for hydrogen. And then, okay, let's try helium. Just 2 electrons. Doesn't work. So, nice try, Bohr, but didn't work out. Okay, that's enough for today. We'll get into the really crazy stuff on Monday.